So sometimes when we rotate a region, we get an object whose cross-section is not a perfect disk, but rather a disk with a hole in it, otherwise known as a washer. So that would occur in a situation like this. If I just were to sketch a region, for instance, that looks something like this. Now you rotate that region, and you end up getting this almost vase-like looking. I'm going to try to kind of sketch the other half of it, and this almost looks like Pac-Man from this angle. But if that rotates around, you can see that the cross sections, if you were to cut this, the cross section would form a washer. And so what we're going to do is analyze the washer and figure out the volume of the washer. The first thing to notice is that a washer will have two radii, a small and a large. And then the area of the face of this washer is going to be, it's the area of the big circle, so it's pi r squared, pi big R squared, minus pi little r squared, because you want to subtract the area of that white section. And then to get the volume, you would just times by the thickness, which depending on the how the region is situated and how you drew your rectangle and what axis you're rotating around, would either be dx or dy. So I'm just going to put a dx there for now. So let's do an example. The region in the first quadrant enclosed by the y-axis and the graphs of y equals x squared and y equals x is revolved about the x-axis. So let's sketch that picture. Y equals x looks like this, and y equals x squared looks like this. So I didn't draw everything, but I just drew the important region. And we know that these are going to intersect at the point 1, 1. So we're rotating this around the x-axis. So I'm going to draw a vertical rectangle, and imagine what happens when I just rotate that vertical rectangle around the x-axis. So when I do that, I end up getting my washer. Alright, and it's a vertical rectangle, so its thickness I need to call dx. And now I've got to deal with what little r and big R are. So let's go to the picture. Little r is going to be this distance right here. Right? So if you imagine we're looking at the washer sideways, if I drew the other half of the washer, you get this picture here. Right? You can see that black section there, that's my little radius. And my big radius would be this distance. So my little radius is actually the distance from the x-axis to this curve right here. Now that curve is x squared. So the coordinates of that point there are x comma x squared. So I'm going to zoom in and draw that. And while I'm at it, I'll draw the coordinates of this point, which will be important. That has coordinates x comma, and it's the curve y equals x, so it's x comma x. Notice that I named the points in terms of x because I drew a vertical rectangle. I'm integrating with respect to x, which means I got to name everything in terms of x. So what that means is little r is going to be that y coordinate, which is just x squared. And big R is going to be x. And so now the volume of this is just going to be the area of the face, which is pi big R squared, minus pi little r squared, times the thickness dx. And therefore the total volume would just be the integral from 0 to 1, 0 to 1, as x goes from 0 to 1, of pi x squared minus pi x squared squared. You can write that as x to the fourth dx. All right, so there's an example using a washer. So it's really it's a disk, but it's almost as though you do a disk method analysis, and then you subtract you have to subtract the hollow part of the middle, which is represented by that inner circle there. So we'll do a couple more examples of this. So this says the region in the first quadrant enclosed by the y-axis and the graphs of y equals x squared and y equals x is revolved around the y-axis. Find the volume of the solid formed. So as usual, we draw the region. So it looks like it's the same region, y equals x and y equals x squared. And we're rotating that around the y-axis. So I'm going to draw this time a horizontal rectangle. And again, that's because you always want your rectangle to be perpendicular to the axis of rotation if you're going to use the washer or the disk method. And so when you do that, you get a washer. And it's a horizontal rectangle, so I got to call its thickness dy. Which means that my big R and my little r are going to have to be written in terms of y. So let's go to the picture and see if we can figure out what big R and little r are. This distance here, notice I start the distance from the axis of rotation. You'll always be able to figure out your radius by doing that. This is little r, and this is big R. So how do we figure out what those should be represented as? Well, let's zoom in on this point right here. That point has coordinates. So yes, this is the line y equals x, but if I want to name that point, I'm going to name it y comma y, right? Because the y coordinate is the same as the x coordinate if it's on the graph of y equals x. And I'm going to name this point here, not x comma x squared. Its name in terms of y would be square root of y comma y, right? And again, that's just if you solve this equation up here for x, the x coordinate is the square root of y and the y coordinate is y. So with that in mind, we can now describe this distance, the little r, as just y, right? And because that's just the x coordinate of this point minus the x coordinate of this point, which is y minus 0. And big R would have a radius of square root of y. And so therefore the volume would be pi big R squared minus pi little r squared times dy. And therefore the total volume would be the integral. And we're integrating with respect to y this time. Fortunately, this 0.11 sort of makes it symmetrical, so whether you're integrating with respect to y or x, it's still the integral from 0 to 1. But these are y values, so I'm just going to emphasize that. Y goes from 0 to y goes to 1. Of pi square root of y squared, I guess I'll write that as pi y, minus pi y squared dy. And this will give you the volume of that washer. I'm going to put a link to a video that describes how washers come about, or it gives you a nice animation of the washer method, which I think might just bolster your understanding a little bit.